Hi, I'm Miss Hearn. Let's get started. In this question, we're asked to find dp dq, and the function is p equals 2q sine q, all divided by q cubed minus 1. So this is an interesting problem because if you take a look here, let's zoom in a little bit. All right, we have a product of two functions of q, here and here. And then that product is being divided by a function of q. So we have both a product and a quotient. So let's remember our product and quotient rules. So the product rule says that if you have a function f of x, which is equal to a first function of x times a second function of x, we'll call them capital F for first and capital S for second. Then the derivative of the product is the first part of the product times the derivative of the second plus the second part of the product times the derivative of the first. This is called the product rule, and it applies anytime you have something with a variable times something with a variable. So in this case, it's actually f of q and s of q. It's functions of q, but the same idea applies. And then we also have a quotient. So when we have a quotient, we have to use something called the quotient rule. And the quotient rule says when you have a function that involves division of two separate functions, something with an x divided by something with an x, or in this case, something with a q. So we're going to think of this in terms of the bottom. So we're going to think of this in terms of the top function t of x divided by the bottom function b of x. So when you have a function of this form, its derivative will be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Bottom d top minus top d bottom over bottom squared. So the product occurs within the quotient. So what I'm going to do is I'm going to think of this as being my top function, and this is going to be my bottom function. And so I know that I'm going to use the quotient rule, but in the process of finding t prime, the derivative of the top, I'm going to have to apply a product rule. So here we go. So if t of q is equal to 2q times the sine of q, let's go ahead and find t prime. In order to do that, we are going to identify the first part of the product as our f and the second part as our s. So our product rule tells us that the derivative of t is going to be the first times the derivative of the second plus the second times the derivative of the first. So let's go ahead and find f prime and s prime. F prime is going to be the derivative of 2q, which is just going to be 2, and s prime is going to be the derivative of sine of q, which is going to be the cosine of q. So t prime of q, the derivative of the top, is going to be the first function, f, which is 2q, times the derivative of s, which is cosine of q, plus the second function, which is sine of q, times the derivative of the first function, which we figured out was going to just be 2. So t prime of q is just 2q cosine q plus 2 sine q. All right, so to find the derivative that we want, p prime, we have to use the quotient rule, and we need both the t prime and the b prime. So let's go ahead and find b prime as well. So we decided to let the denominator be the function capital B, the bottom. And so that was q cubed minus 1. B prime of q would be 3q squared plus 0. So now we know that b prime of q, the derivative of the bottom, is just 3q squared. Okay, so our original function p is 2q sine q over q cubed minus 1. We've divided the function into a top part and a bottom part, and we have found the derivatives of the top and the bottom. And now to find the derivative of the whole function p, we need to use the quotient rule. Bottom d top minus top d bottom over bottom squared. P prime is going to be the bottom, which is q cubed minus 1, times the derivative of the top, which we found to be 2q cosine q plus 2 sine q, minus the top, 2q sine q, times the derivative of the bottom, which is 3q squared, all over the bottom squared, q cubed plus 1 squared. Now this is really our derivative, but generally speaking, we don't leave it in this format. We would normally look to see if there's anything in this big term and this big term that matches up that we could factor out, but the only thing that I see there is a common factor of 2, which isn't really that helpful. So I'm going to go ahead and just multiply out the two terms and see if we get any like terms that we could possibly combine. In other words, I'm going to multiply q cubed to each of these two terms, and you can think of it as foiling, and then multiply the -1 times each of the two terms. So when we do that, we're going to get p prime equals q cubed times 2q is going to be 2q to the 4th cosine q, and q cubed times 2, so we're just going to have plus 2q cubed sine q. And then now distributing the -1 to each term, we're going to just get the opposite. So we're going to have minus 2q cosine q minus 2 sine q. And then of course here at the end, we just want to multiply the 2q times the 3q squared. So we're going to have minus 6q cubed sine q. And this is all over q cubed plus 1 quantity squared. And now look for any like terms. So to be like terms, we need exactly the same variables with exactly the same exponents and the same trig function in this case. So 2q cubed sine q and negative 6q cubed sine q, those are the only two like terms that we have. Let's go ahead and combine them. So we have p prime equals 2q to the 4th cosine q. 2q cubed minus 6q cubed is negative 4q cubed sine q. And then we have minus 2q cosine q and minus 2 sine q tagging along there, all over q cubed plus 1 squared. Now in the numerator we have 4 terms, and we could try using grouping, but I've looked it over and I can see that we're not going to come out with any common factors by using grouping, so I'm just going to stop here. So this is a good example. It's not pretty, but a good example of where we use both the product rule and the quotient rule to find a derivative. I hope you found this video helpful. If you did, please remember to like it. That helps other students to find the video.